Hi guys, welcome to IGCSE on Fingertips. I am Divyang and today we are going to learn states of matter, atoms and atomic configuration. Let's start with states of matter. What is a matter? Matter is something that occupies volume in space and has mass. Matter can be element, compound or a mixture. The material may be any of these. It can be in a state of solid, liquid or gas, and it can be made of atoms, molecules or ions. We will call them particles throughout our study. Now, different states of matter are solid, liquid and gas. Solid has definite volume, it has a fixed shape. Because it has a fixed shape and definite volume, right? The particles, we know that the particles are close to each other. Because the particles are close to each other, their density is high. Because they have fixed shape, they are unable to flow. What can flow? Liquids and gases both can flow. Now, particles in liquid are enough have enough space between each other that they can flow past each other, right? Because they can flow past each other, they do not have definite shape, but they do have definite volume. But in gases, the particles can move around freely. Because they can move around freely, they don't have definite volume, they don't have definite shape, and their density is very low because the particles are far away from each other. We can achieve changes in state. We can make a solid into a liquid into a gas. For this, we always have to remember that all matter is made of particles. Now, if I apply heat to particles, the particles will start to vibrate more vigorously. They will move apart. When they move apart, the change of state occurs. Let's have a look at this. So I can change a solid to a liquid. The process is melting. This happens at melting point, right? The liquid can change to gas in evaporation or vaporization. The solid can be directly changed to gas using sublimation, right? If you are going from the lower level to a higher level, the temperature is increasing. You are applying heat. The energy is given to the state of matter, right? Now, if I want to go from gas to liquid, if I want to make a gas into a liquid, I'll either have to do condensation or liquefaction. If I want to make a liquid into a solid, it is freezing or solidification. Gas to solid is again sublimation, right? You have all the definitions over here, and you will be able to download these notes from the description of this video. I will upload a PDF of this notes in the description, right? Now, all of this changes occurs. We can record these changes, right? There are some definitions for you to go through when you're reading the notes. But over here, let's say that I am cooling a gas to make it a solid, right? What happens is, when I start with gas, as the time passes, right, I'm removing heat, I am cooling down the gas. Slowly it starts becoming liquid. If the gas is pure, the gas becomes liquid at a fixed temperature. This temperature is known as condensation. Sorry, this temperature is known as condensation point. The process is known as condensation, right? Here, during condensation, why is temperature not changing? Because all the heat that is lost by particle is right now changed to forces in the particles. So particles come closer to each other, right? We have understood that every particle, every matter is made of particles. These particles start to vibrate when they are in solids. If they are in liquids, they can move past each other, and in gases, they can actually move freely. So these free moving particles, heat is removed from them, energy is removed from them, so they move slower and slower, and finally the intermolecular forces are established. Here, over here, the temperature is not changing. This is a sign of a pure substance. The same happens for solid, right? When it is going from liquid to solid, the same thing is happening. Now, if it was asked to me that what is condensation point, it goes from gas to liquid at somewhere around 74 or 75 degree. So for me, condensation point is that. And At around 20 degree, it goes from liquid to solid. So that is the freezing point of this substance. Now, inverse of this is a heating curve. This is heating curve for water. If I had taken ice at minus 25 degrees Celsius, what will happen? If I apply heat to it, the ice will go on heating till 0 degree. At 0 degree Celsius, ice will start melting. But until unless all of the ice is melted away, the temperature of ice and water mixture, right? As soon as ice starts melting, there will be water inside it. The ice and water mixture does not change its temperature until unless all the ice is broken down, right, to liquid water. Now, where does this energy go? I am applying continuous energy. Where does this energy go? This energy goes into breaking the intermolecular forces and moving the particles further apart, right? Now, if you notice, when boiling takes place, the time taken is greater, which means more energy is used up in breaking the intermolecular forces, the bonds, to move apart particles from each other. So liquid to gases requires more energy compared to solids to liquids, which tells us that in liquids, when they go to solids, more energy is required to break the bonds. Then let's understand the particle theory in detail. As I've already told you, everything is made of particles. Now, a simple proof of this thing is if you observe rusting, right? If a piece of iron is rusting, the whole piece does not rust immediately. Smaller regions of iron rust. This means that iron is made of smaller particles that are reacting slowly, right? So, John Dalton gave us the theory with this thought process that everything is made of particles. Particles are in continuous motion. Solid particles can only vibrate at their own place because the intermolecular forces are so strong they can vibrate their own place. Liquid particles can move past each other and gas particles can move freely because the intermolecular forces are negligible. This shows the path of a gas particle. It can move in any way it wants. It bends only when it collides with other gas particles. So another thing to add here is collisions are continuously taking place in any gas that we observe. Now, what happens to this continuous motion when the temperature increases, and what happens to the volume of gases? So when the temperature increases, right, temperature is the average kinetic energy of particles. So when the temperature increases, these particles move more vigorously. When they move more vigorously, they uh, collide more often. When they collide more often, they try to move apart and the volume of the gas increases. If I increase the temperature, volume of a gas that can freely expand, its volume will always increase. When pressure increases, let's have taken a gas and I am applying pressure, let's say inside a balloon, right? I'm trying to compress a balloon. What will happen? They come closer and hence the volume of the gas decreases, right? Then how does diffusion takes place, right? What is diffusion? Diffusion is the movement of particle from their region of higher concentration to their region of lower concentration, and this happens due to collision. Now let's take for an example, I have added some crystals of KMnO4, right? I have added some crystals of KMnO4 inside the base of this beaker. What will happen? Water particles are also under continuous motion. These water particles will continuously collide with crystals of KMnO4. When they collide with crystals of KMnO4, some of those particles from solid, right, they will be dissolved into water. Slowly, slowly, a lot of particles start dissolving in water. So, dissolution has taken place. Now, all the KMnO4 particles that were solid, that were attached to each other due to high intermolecular forces, are now between water particles. They are dissolved in water. As soon as they are dissolved in water, the KMnO4 particles also want to move, and the water particles are also in continuous motion. This collision leads to spreading of particles, right? It goes from a region of higher concentration to a region of lower concentration. Now imagine a lot of people, are standing in one corner of the room, right? If they are continuously moving, they will try to go in different directions and increase the space among them, right? So if you can imagine, imagine the same thing with a particle. Let's look at it like this, that let's say there are a lot of particles together over here, right? This particle wants to move. So if it moves in this direction, it collides with another particle and hence changes its direction. It will keep on moving in that direction until unless it collides with another particle again, right? So if a lot of collisions are taking place in this small space, the particles will eventually move out, which is the reason why diffusion happens from a region of a higher concentration to the region of lower concentration. Now, as I've already told you, that first dissolution will take place. For anything, first the particles will dissolve in the liquid and then they will be diffused to all the corners of the liquid, right? This is another example where air and bromine are mixed with each other. What will happen? Bromine will be diffused throughout the column of the air inside these two test tubes. Now, let's let's see what is an atom. Atom is the smallest indivisible particle of a substance. Anything, mixture, compound, or an element is made of atom. Solids are made of atom, liquids are made of atom, or even gases are made of atom. Now, what is atom? It is the smallest indivisible part, right? An element has all atoms of same type. So, if I take gold and I look at each element of gold, all the atoms of gold will be exactly same, right? It is also that each atom of gold will exhibit the same properties as gold. It will have same physical properties as gold. It will have same chemical properties as gold. If gold does not react with oxygen, gold atom will also not react with oxygen. So the idea of reaction, the idea of behavior, the idea of what happens to the element can be studied by studying the atom of the element. A compound has atoms chemically bonded in a fixed ratio. So, if we look at carbon dioxide, for example, oxygen is bonded to carbon and there are two oxygen bonded to each carbon in one molecule of the carbon dioxide compound, right? Then a mixture has atoms or molecules mixed physically in a random number. So our atmosphere, it has oxygen, it has carbon dioxide, it has nitrogen. Now we know that there is approximately 78% nitrogen in our atmosphere and 20%, 21% of oxygen. But if I were to take a sample from this class and check that what is the percentage of nitrogen and percentage of oxygen, it will be a little bit different from the number that we have approximately found out. The reason behind this is very simple, because the nitrogen, oxygen, carbon dioxide, argon, whatever is found in our atmosphere is actually not distributed evenly. It is in random number. It is a mixture, right? Then what does the atom itself consists of? Atom consists of protons, neutrons and electrons. Protons are positively charged particles, neutrons are neutrally charged particles. Protons and neutrons are inside the nucleus of the atom. Electrons are on the outside of the nucleus of the atom. It looks something like this. This is the nucleus. It contains protons and neutrons. This is the outside of the nucleus. It contains electrons. The whole thing is an atom. Now, what is the mass? We say it's 1 unit comparatively. Compared to what? Compared to other protons right now. Okay, so what we do is either I can write down the mass of the whole proton, which becomes a larger number and is difficult to calculate and intuitively understand a lot of things. So what we'll say, that proton has a 1 unit of mass, neutron has a 1 unit of mass, but electron is almost massless. But proton has 1 unit of charge, electron has opposite negative unit of charge, so protons are positively charged and neutrons are neutrally charged. They do not have any charge in them. Now, atomic number and mass number. Now if you think about it, if you look at periodic table, right, the first element in the periodic table is hydrogen. Hydrogen has one proton. Any atom that has just one proton is going to be hydrogen. So the number of proton becomes the identity of the element. If the number of proton is 3, it is always going to be lithium. So number of proton is again identity of an element. So accordingly, we said the atomic number should be the number of protons in an element. It is also sometimes known as proton number. So atomic number and proton number are the same thing. We identify atom from the number of proton, and hence we call the number of proton as atomic number. Now because the nucleus is what contains the neutrons and protons, and as we have just seen that electrons do not have any mass, so the mass of atom is dictated by the number of neutrons and protons inside the atom, and therefore we say that the mass number is the total number of protons and neutrons in the atom, right? Sometimes mass number, or I've written also known as mass number, should be nucleon number because it is also equal to the number of nucleons. Okay, then we have electron number. It is the number of electrons in an atom, but for an atom it is always equal to the number of protons. And if you look at any atom is neutral, right? You look at any atom anywhere in the universe, if it is an atom, it has to be neutral. The fact that it is neutral tells us that the number of protons and the number of electrons have to be equal. Protons are positively charged and electrons are negatively charged. If they are unequal, there will be charge on a atom. Then it will be known as ion, right? We will look at ions in the coming videos, but right now atom is neutral. The number of protons and the number of electrons is always equal, right? Then we have relative mass, right? First, let's see. Relative mass of an atom is the average mass of naturally occurring atoms of an element on a scale where carbon 12 has a mass of exactly 12 units. Now, what does this mean? It means that simply, for me, let's say this calculator has 1 unit of mass, right? Now, if this pen, I weigh this pen with this calculator on a balance, right? Let's say I have a balance, and on this I keep 8 pens, and the mass of 8 pens is equal to 1 calculator, right? If calculator is my standard, I will say that the mass of 1 pen is 1/8 of the calculator, right? This is how we found out the mass of each of the atoms, each of the elements that we know of. So we said that, okay, carbon 12, most abundant element in nature, right? We will name it that it has 12 units. Now if I take hydrogen, 12 hydrogen will be required to weigh or balance carbon 12, which means hydrogen has a mass of 1. If carbon has a mass of 12 on this scale, hydrogen has a mass of 1. It is as simple as that. Why do we say carbon 12? Because it has 12 nucleons. Should this also relate that each nucleon has a relative mass of 1, right? So that is the understanding where we said that the mass of neutron is 1 unit and proton is 1 unit, because carbon 12 also has a mass of 12 units, right? Now sometimes it so happens in nature that, let's have a look at neon over here. Now neon sometimes has 10 neutrons, sometimes has 11 neutrons, and sometimes has 12 neutrons, right? So let's say if I take a jar of neon from nature, right, after fractional distillation, if I take a jar of neon, 90.5% of the atoms in this jar will have 10 neutrons, but 0.3 percentage of them will have 11 neutrons, and 9.2 percentage will have 12 neutrons. In this case, when I tell you the mass of a neon atom, I cannot say the mass of a single neon atom. It is inconvenient for us to write these percentages every time. So what we do, we find out the relative atomic mass according to abundance. This 90.5%, 0.3% and 9.2% is relative abundance. So let's have a look at it from the perspective of chlorine. So we are going to find the relative atomic mass of chlorine. Okay, what is the percentage of each masses? So chlorine has two isotopes, right? Same number of, oh sorry, I think I forgot to say this, that the if the number of protons are same but the number of neutrons are different, which means the atomic number is same but mass number is different, these type of elements are known as isotopes. Whenever the abundance of isotope is considerable, right? In case of chlorine, one isotope is 75%, the other one is 25%. Whenever the relative abundances are very what do you say, close to each other, or rather significant, we would try and find out the average atomic number, right? So the fact that atomic numbers, sorry, average mass number, and the fact that the mass number in your periodic table for chlorine is 35.5 tells us that there are isotopes of chlorine. When you grow up and look at mass number from Google, you will find that almost every element has a mass number in a decimal, which means that almost every element does exist as a isotope, right? So chlorine has two isotopes. One has a mass of 35, the other one has a mass of 37. The one that has mass of 35 is 75% abundance. So in one jar of chlorine, there will be 75% of atoms having mass of 35 and 25% of atoms have a mass of 37. Now how do I find relative abundance? The total abundance is 100, right? There is 100% of chlorine in that jar. So 75 into 35 upon 100 plus 37 into 25 upon 100, right? This will give me 35.5, right? Let's check if the data is correct. So 35 into 75 plus 37 into 25, right? It is actually 35.5. So that is the relative atomic mass of isotopes. Let's have a look at configuration. Now we have understood how are protons inside the nucleus of an atom, neutrons inside the nucleus of an atom. What can happen? Proton is the identity, neutron gives the mass with the proton. Both of them are in the nucleus. What happens to electrons? Electrons tell us the chemical properties of an element. Why? Because first, let's understand the arrangement, then I'll tell you how does electron affect, the number of electron affects the chemical properties of an atom. Now, electrons are segregated into shells, right? The first shell can contain only 2 electrons. So, let's think about, let's say that an atom has 20 electrons. All of these 20 electrons are not at the same place. If you think about protons and neutrons, if this atom had 20 protons, right? If I am saying it has 20 electrons and I am saying that it is an atom, it must have 20 protons. All of these 20 protons are together at the center of the atom. It may have 20 or 21 or 19, any number of neutrons, but these neutrons are also going to be at the center. Electrons are not together, they are distributed around the nucleus. Okay, this distribution has some rules. So let's think about it like this, that in a stadium, just like there are seats, right? There are rows of seats. Similarly, the electrons are distributed around the atom. In the first row, the first shell, there can be only 2 electrons. In the second, there can be only 8. In the third, 18, the fourth, 32, and the fifth, 50. Now see, you don't have to remember all the numbers, you have to only remember these three, that the first shell can contain 2 electrons, the second can contain 8, the third can contain 18. This comes from the fact that the number of electrons are decided by the rule 2n square. We observed the electrons and we found out that the relation is 2n square, where n is the number of shell. So first shell, 2 into 1 square is 2, 2 into 2 square is 8, 2 into 3 square is 18. Now, why is this important? Because if we look at sodium, right? Sodium has 11 electrons in the atom because it has 11 protons. Now, if you look at the configuration, then it can have only 2 electrons in the outermost shell. It is still left with 9 electrons. So, it will have 8 electrons in the, sorry, I said 2 electrons in the outermost shell, 2 electrons in the first shell. It has 8 electrons in the second shell and it has 1 electron in the third shell, right? Now, if you observe this particular shell is not stable. Why is it not stable? We'll come to it. But look at chlorine. Chlorine has 2 electrons in the first shell, 8 electrons in the second shell, 10 are already filled and 7 electrons in the third shell. If you look at neon, it has 2 electrons in the first shell and 8 electrons in the second shell. Now, by nature, we have observed that the elements that have 8 electrons in their outermost shell will be stable. They don't want to react with anyone else. These type of elements that do have 8 electrons in their outermost shell are known as noble gases. One exception where the noble gas has only 2 electrons in the outermost shell is helium. Because its outermost shell is full, it also acts as a noble gas. It does not react with anyone else. Now, what about the rest of the elements, right? Only handful of elements will have their outermost shell with 8 electrons. What about all the other elements? All of these other elements want to achieve the nearest noble gas configuration. So they can either accept electrons or donate electrons and want to become compounds, right? We will see how compounds are formed and we will see different types of compounds in the coming videos. But here, what do we need to understand? That if the configuration is not resembling a noble gas, the element by its nature wants to go to the noble gas configuration. When it wants to do this, it will react. So reactivity depends on the number of electrons and the configuration of electrons, these two things. Now, if you notice, the isotopes have same number of protons and therefore same number of electrons. When they have the same number of protons and electrons, they will also have exactly same electronic configuration, which leads to the fact that isotopes have same chemical properties. These type of questions are asked in your boards. So please specify this. They have same chemical properties because they have same number of electrons and hence the same electronic configuration, right? And then last but not the least topic over here is notation of elements in periodic table. And what is periodic table? See, basically periodic table is where we write down all of our elements, right, in some logical form. What is that logical form? If you look at electronic configuration, right, the number of electrons in outermost shell is known as valence electrons or valence electrons, right? If elements have one electron then in their outermost shell, they are arranged in a single group, a vertical column, right? This is known as group. So lithium will have one electron in outermost shell, sodium, potassium, rubidium, cesium and francium, all of them will have one electron in their outermost shell. The same goes for neon, argon, krypton, xenon and radon. All of them will have 8 electrons in their outermost shell because they are in the 8th group. The only exception over here is helium. We are placing helium over there because helium has its outermost shell full, which means it is a noble gas. Now, the number of shells tell us where to keep the element in the period, right? So, potassium has 1, 2, 3 and 4 shells, and potassium also has one electron in its outermost shell. So the relation between the electronic configuration and the place of an atom in the periodic table is very clear to you, I hope. Now once that is clear, sorry, once that is clear, right? So can we now understand how to note an atom or an element according to the periodic table? So what you will find is Mn, right? I'm talking about this element. Mn manganese has a mass of 55 and atomic number of 25. So this is how atoms are shown. This is how elements are shown. But let's say potassium. It has lost one electron, right? So potassium, now what happens? Initially, potassium has 19 electrons and 19 protons. Now, if it loses one electron, the number of proton is 1 greater than number of electrons. So, the all over charge on potassium is positive and the mass number remains same because the number of protons and neutrons are going nowhere. Look at magnesium. What happens? Magnesium has a symbol Mg, right? Subscript the number of, oh, sorry. I think I should write it somewhere else. Let's write it over here. So I have Mg magnesium, the symbol. 12 is the number of protons, right? Or the atomic number. 24 is the number of nucleons or the, what do you call it, mass number. If it has lost two electrons, I will write it as 2 plus, right? From here we also understand one more information, that using all of this you can also find the number of neutrons. The number of neutrons is going to be difference between the atomic number and the mass number. For magnesium, that is 12. But let's come to phosphorus, right? Look at phosphorus. So I can write phosphorus as P over here. 15 is the number of protons. 31 is the number of nucleons. This means that the neutron number is equal to 31 minus 15, which is 16 neutrons, right? Let's say phosphorus has gained 3 electrons. Here they were losing electrons, right, to get to the nearest noble gas configuration or to become stable. Here phosphorus gains 3 electrons, so it has a charge of 3 minus, right? We will get some tabular questions, right? I will try and attach some questions with these notes at the end of the description. Please let me know if you need anything else in this chapter. Thank you for watching. Bye bye.